Hello everyone, I'm very happy to give this talk on my result, classical verification of quantum computation in linear time. I'm Jiayu from Caltech. This talk will be divided into 3 parts: background, results, and techniques. So what is classical verification of quantum computation? In this problem, L is a quantum circuit C, and it wants to evaluate it and get C0. But it's a classical client, so it wants to make use of a quantum solver to evaluate the circuit. So it sends the circuit to the server, and the server returns the response. But it doesn't trust the server because the server might be an attacker who try to convince it a wrong result. So it wants to install a protocol to interact with the server and get convinced of the result, or catch the server cheating. This is a fundamental problem in quantum cryptography, and it's the foundation of secure quantum computation protocols, which means it has a strong practical motivation. In more detail, there are 3 requirements: correctness, soundness, and efficiency. For completeness or correctness, it means if everyone is honest, the honest server should make the client accept a right result. And soundness means no efficient server could convince the client on a wrong result. Here, by only considering the efficient server, we could rely on cryptographic assumptions. And finally, we want the efficiency requirement, which means both parties should run in polynomial time. There are many details for this problem. In the early stage, people consider a weakened setting where the client has a small quantum device, which means the client could prepare and send many quantum states or receive ephemeral quantum states. In this setting, we can get unconditional soundness, like what is given in these papers. In these protocols, the total client-side quantum computation would be linear to the size of the circuit. But because the client still needs to do quantum computation, it seems hard to implement in practice at scale. And the second setting that people consider is the setting where there are 2 non-communicating servers. In this setting, we already know the client can be completely classical, and we can get unconditional soundness. And this line of work has led to many celebrating results, like the characterization of MIP stack complexity class. But this class of protocols still seems hard to implement in practice at scale, because it might be hard to keep 2 remote servers not communicated by a long time. A relatively recent approach is to use crypto to get the soundness. But the work of Mahadev 18, we know we can use a single quantum server and a classical client to get soundness based on crypto assumptions. Hopefully, these kind of protocols could be implemented in practice in the era of error-critical quantum computer. The work of Mahadev 18 has led to a great success. Here, CVQC means classical verification of quantum computations. This paper has led to a lot of studies. For example, people study how to improve the original CVQC protocol in different ways, like these papers. Or people constructed multiparty quantum computation protocol and zero knowledge protocol quantum computation in these papers. And people studied many more advanced problems like obfuscation and so on. All of them are fundamental cryptographic primitives, and the classical analogs have been widely used in practice. So we have a lot of protocols, which is good. But is this the end of the story? Let's take a closer look at the Mahadev 18 protocol. Suppose that the client has a quantum circuit C, and you want to evaluate it by the protocol of Mahadev 18. So what will the client do in the protocol? If we take a closer look at the protocol, we will notice the client needs to ask the server to run a quantum circuit that is of cubic size in the original circuit. So imagine what will happen in practice. In practice, the server might say, oh, building a quantum computer is already very hard. We don't want to run a cubic time protocol. So let's go back to the diagram. If Mahadev 18 protocol has cubic time complexity, that implies all these protocols in the diagram that people already have already cubic time in the standard circuit. And this burden is in terms of server-side quantum computations, which is big burden in practice. So everything here is in cubic time. And here comes our results. We can run CVQC protocol, a classical verification of quantum computation protocol that runs at linear time in the standard circuit. In more detail, we can run quantum computation verification protocol, which is, as in the setting of Mahadev 18, use only a completely classical client, zero quantum server, and assuming Qcrypt assumptions. Here we assume the following Qcrypt assumptions. One assumption is the existence of noisy tropical Qcrypt functions, which is raised in BCMVU paper and is extensively used in quantum crypto nowadays. And this assumption could be constructed from learning with error assumptions. Learning with error is a very famous post-quantum crypto assumptions. And we also assume the quantum random oracle model, which is raised in this paper, which is also an extensively used assumption in quantum crypto. In practice, we can replace the random oracle model by hash functions asymmetric encryption, which is reasonable assumption. And our protocol has linear time complexity. And this time complexity includes the total time complexity of both the client and the server. So hope that our protocol could be a beginning of a new story. Return to the diagram. If we replace the CVQC by our linear type CVQC protocols, it naturally leads to a series of questions. We wonder whether all these protocols could be taken to linear time. And furthermore, we wonder whether these protocols could be taken into practice. So in that part, we discuss our techniques. So let's take a look at the existing works. So where's the blowup in existing works? The Mahadev 18 paper, they take the Hamiltonian approach. They take in this approach, they need to first transform the circuit evaluation problem to a Hamiltonian growth estimation problem. But this transformation has a blowup, which means the Hamiltonian growth estimation problem has an inverse quadratic promise gap in the side of the circuit, which means to use this approach, the client and server need to do quadratic round of sampling. And each round of sampling requires linear time to prepare the ground state. So it's qubit time in total. And we take a different approach, which is a remote state preparation. So what is remote state preparation? In this problem, instead of verifying a circuit, we consider state family F. Alice wants to send a state phi randomly sampled from this state family F. So ideally, Alice could prepare the state and send it to the server through quantum channel. And finally, Alice could get the description of the state. The server simply holds the state, but could not get full information of the state. And the problem asks whether we can implement this ideal task by some other channels, for example, classical channel. So what we want is as follows. The client interacts with server classically to instruct the server to do something on its own. And finally, if the server could pass the protocol, the joint state should be of the client and server should be close to the ideal state, where the client knows the description of the random state from the state family, and the server simply holds the state, but does not know anything else. In the cryptographic setting. So why should we care about this problem? The reason is, if we assume the client could prepare and send simple quantum states to the server, then we know how to verify quantum computations. And we have relatively efficient quantum protocols in this setting. People have a lot of work in this setting, like these papers. And finally, in the FKD paper, they constructed a protocol where the client only needs to prepare and send states in the plus theta states, where plus theta means 0 plus e to I theta pi 1, where theta is from 0 to 7. There are 8 possibilities. And the total number of these states is only linear to the side of the circuit, which means if we could replace the prepare and send step by classical channel remote state preparation step that runs in linear time, the final overall protocols will be a classical verification quantum computation protocol that runs in linear time. So let's take a look at existing protocols of classical channel remote state preparation. Suppose the total number of gadgets that we want is L. People have also done a lot of work for these problems. For example, in the GV19 paper and the CCKW19 paper, also constructed protocols that are powerful enough for preparing the plus theta states. But the problem with this protocol is they require the time complexity of these protocols is either estimatedly big or very big, which is possibly L to the 40 or 100. And it also requires large round complexity. And relatively recently, the GMP 22 paper and FLC 52 paper make further progress in this problem. They studied composed versions of their predecessors. But in this protocol, the time complexity is still very big. And the round complexity is also roughly the same. Because that it didn't work for CVQC protocols could run in qubit time. So it seems that the remote preparation protocol seems to be even more difficult than CVQC. So possibly, previous people does not consider it as a promising approach. But we take this approach and get the following result. We construct remote preparation protocol that allows us to prepare L states in the form of plus theta, which means in the end of the protocol, the client will get theta 1 to theta L, random sampled from 0, 1 to 7 to CL. And the server should get plus theta 1 to plus theta L, restricted on the passing space. The time complexity of our protocols is linear to the number of states that we want to get. And initially, our protocol runs in constant runs, which means our protocol good to use in many different places. And as said before, our protocols require critical assumptions, which is noisy trapped correct functions and quantum random outcome model. And by composing this protocol with FKD protocol, we get a linear time CVQC protocols. In summary, we get a classical quantum computation protocols that runs in linear time in the southern circuit. And along the way, we constructed a parallel remote preparation protocol for plus theta states that runs in linear time and constant runs. We expect our results and techniques could find more applications in different problems. And hopefully, our results, together of further works, will help potential practical impact in the error-corrected quantum computation area. Which is important in practice. Thank you very much.